In chapter 15, we're going to keep talking about reactions, but now we're going to talk about equilibrium conditions. So we're going to talk about a special case or special point in time where we're dealing with our reactions. So chemical reactions are going to reach this state of dynamic equilibrium. So we call it a dynamic equilibrium to really emphasize the fact that we're at equilibrium, and equilibrium means that the concentrations are essentially constant of all the substances involved in our reaction. But we call it dynamic equilibrium because it means that the concentrations are constant because the rate of the forward reaction is equal to the rate of the reverse reaction. So we're going to be looking at all of our reactions now with this little double arrow. So we're going to be representing our reactions in terms of a forward reaction. And in the forward reaction, these are our reactants and these would be the products. And then if we think about that in the reverse direction, the reverse reaction, this ammonia would be the reactant and these would be our products. So we're going to be talking about situations where we maybe adjust one substance or add more or change a condition. And we want to know, how does that change that equilibrium concentration? How does that of our substances, our reactants or products, or does that drive the reaction to go in the forward direction? Does it drive the reaction to go back in the reverse direction? So one of the main things we want to recognize in terms of, again, that dynamic equilibrium, that means that the rate forward, so the rate that we're going in the forward direction is going to equal the rate in the reverse direction. So both are still happening. We have this reaction, so we're making that ammonia, and that ammonia is breaking back down into nitrogen and hydrogen. It's just that those things are happening at the same rate, so we end up with an equilibrium or constant concentration. So here's a graph showing what we might see if we plot concentration as a function of time. So that black line, so that would be, say, our ammonia. So if we describe this reaction, starting with just our reactants is written in the forward direction, so nitrogen and hydrogen. So we don't have any ammonia to start with. As time proceeds, we increase that concentration of ammonia and we decrease. So we could say that maybe this is N2 and this is my hydrogen. Once we get to that point out here where these concentrations are essentially the same, and maybe I didn't make those quite flat enough, those concentrations quit changing, that's going to be our equilibrium, right? This is the point where we're going to now be talking about in chapter 15. All of this before that point, so this is non-equilibrium conditions. So you can see that those concentrations are still changing with respect to time. So we're going to define something called an equilibrium constant. So an equilibrium constant is going to be defined as a big K. So remember we used a little k in chapter 14. This was our rate constant, right, for our rate law. Now we're going to use this big K. So you want to be careful and distinguish between that big K and that little k. So they are gonna mean different things. That equilibrium constant, this is big K. And big K is going to equal, if we look at this reaction here, our hydrogen plus iodine producing 2 moles of HI, we're going to have a ratio. We can set this equilibrium constant as the ratio of the concentration of the products. So in this case, it's just HI raised to that stoichiometric coefficient. So we're going to square that over the concentration of the reactants, again, raised to those stoichiometric, raised to that stoichiometric coefficient. So in this case, in front of that hydrogen and in front of the iodine, we just have one. We don't have anything there. So we would just, if we want to be real explicit, we could put ones up there as a superscript or raise those concentrations to the first power. We tend to leave those out when we're talking about writing out our formulas. So this is something called an equilibrium constant, and it's going to be the same sort of basic ratio every single time. We're going to write an equilibrium constant. We write it in the direction the reaction is written. So we write it for the reaction going in this direction. So it's going to be always products over reactants. And it's going to be concentrations of those products over concentrations of the reactants. And we are going to use that balanced equation and pull those stoichiometric coefficients out and raise those concentrations to that power. So I'm going to skip this because I'm going to talk about these ice tables in a separate packet. So here I just wanted to introduce that K. So big K is our equilibrium constant. We have a general expression that we can use. So if we have just any general reaction, two reactants producing two products, it's a reversible reaction. So I can write that in either direction. That equilibrium constant K that we're defining is always going to be, again, the concentrations of the products raised to those stoichiometric coefficients. So that's my little c and little d over the concentrations of our reactants raised to, again, those stoichiometric coefficients. So this is K. So I'm going to specify this is K for the forward reaction, right? I could also write K for the reverse reaction. And if I do K for the reverse reaction, we want to just recognize that I would flip those reactants and products. So if I'm doing the reverse reaction, then these are my reactants and these are my products. So if I write K for that reverse reaction, we're just going to flip these. So I'm going to have C and D. Those are my products. And then we're going to have A and B. Those are our reactants. So we're always able just to write that equilibrium constant based on an equation that is given or provided for us. So we have a couple of key points that we always want to think about or remember when we're dealing with equilibrium constants, equilibrium conditions. So the first is kind of inherent in the name. If we're calculating K, we have to make sure that we're using equilibrium concentrations, right? We don't want to be using a concentration from, say, this point in time. So at this point in time, we're not at equilibrium conditions, so we cannot calculate this equilibrium constant. The ratio is always products to reactants, so we've already mentioned that a couple of times. So it's easy to kind of remember that's consistent. It's always going to be set up that way. The next piece is the exponents are based on those stoichiometric coefficients. So we're going to use the balanced equation, right? That's what that means there. And then the next one is K is specific for a given reaction. So any reaction I have, I can specify that K, but it is going to be dependent on temperature. So Ks are defined for a given reaction and temperature. So as temperature changes, that K will change. And all this really means at this point is that when you read problems, the problems will say K is blah, blah, blah at 325 Kelvin or something like that. It'll specify a temperature. The units for K are none, right? So K is what we call a dimensionless quantity. So it's not going to have units. There's a section in your book if you want to read a little bit more about this. It's actually dimensionless because units are all canceling. But for our sake and for what we're going to use, just recognize it's dimensionless. So we don't need to include units. When I'm working with a solid, we're not going to include those in the equilibrium constant. So let's say we have, let me see, let's do sulfur. So sulfur plus some oxygen gas, and this is going to produce SO2, and it's reversible. So if I want to do a K for this reaction, it's always products over reactants. So I'm going to have concentration of that SO2 over concentration of, we would have S and O2, but we're not going to use that concentration of the sulfur. And this just has to do with the fact that concentration is not really changing. So if I'm reacting a solid with a gas, we're going to be working with situations where that solid is enough excess that it's not changing in concentration, right? It's not something that is solids are confined to a set space, so they're not changing in concentration in the same context that the other reactants are. So when we calculate a equilibrium constant, we are not going to include any substance in our reaction that is a solid. When we're working with aqueous solutions, kind of a similar note to make, we don't include water. So if I'm working with an aqueous solution, we don't add water anywhere in that equilibrium constant because the water is just present in such a large amount, it's not changing, right? And it's not necessarily part of the reaction. So we don't include water in aqueous solutions. Okay, we also can have reactions involving